Welcome back. So we're going to be talking about uh, bonding and dot diagrams. Again, if you have any questions, comments, problems, please let me know. Um, but let's go ahead and get started with our material for today. So let's talk about valence electrons. So let's consider carbon. How many electrons in total are there on carbon? So let's talk about carbon. Carbon's right here. His atomic number is 6, so he should have 6 total electrons. Now, are they all arranged in the same physical space? Well, no. We know that his electron configuration, based on what we see here, is helium core and then 2s2, 2p2, right? So we know he's got that helium core, and that's his 1s2, and then he's got 2s2, and then 2p2. So he's got 3 different places where those electrons live. The 1s, the 2s, and then the 2p. So there are 3 different places that we've got electrons, right? So 2 electrons in the 1s, 2 electrons in the 2s, and then two electrons in the 2p. And so we know that there are at least 2 different energy levels that we're talking about. And those 2s and 2p are not exactly the same. We're not really sure how they're different, but we know that they're not exactly the same. They're slightly different in energy than they are from each other. Okay, because there's an S and a P and they're slightly different in energy. And we know that from what we did in ALEKS in the beginning. We don't really know how they're different, but we know that they're different. Okay, so cool. We got that. So we know that they're not arranged in the same physical space. Okay. So we've got 2 in that 1s, 2 in the 2s, and 2 in that 2p. All right. So we also know that we have 4 in that 2 level. Okay. And the 2 in those, and the 4 that are in that outer shell, the 4 that are in that 2 level outer shell are the most available to us. So if we're standing on the outside and we're looking at this carbon, those are the ones that I can see. The ones that are on the inside, I can't really see. They're not as available to me. So it's harder for me to get to those ones, and it's harder for me to do anything with them. Okay. So the ones in that 2 level are in the highest energy level. They're the highest quantum number. Okay. Those are the valence electrons. Okay. So those are the electrons that we have for working in bonding and that we can make, bonds with, that we can take away to make cations, that we could add to make anions, things like that. Okay. So those are the things that we could do with those valence electrons. All right. So those are important. Those become very important. And so we need to be able to talk about how many valence electrons there are, because that gives us an idea of how much space we have available to do things like making bonds. How much space do we have? How many can we make? That kind of stuff. All right. So valence electrons become very important. And we've talked about the fact that some things want to lose or gain electrons to become like the nearest noble gas, right? We've talked about the fact that they want to be like a noble gas because noble gases are very, very stable, and we know that just based on their behavior, okay? So we want to be like those noble gases that are way over there on this edge, these guys right over here, okay? So that group 18, these guys are incredibly stable. And the thing about those guys over there is that they have 2 electrons in the S and 6 electrons in the P. And so they have what we call a stable octet. So there's that octet that we want to get to. So everybody wants to have an octet. And that's where that octet rule comes from. Okay, so you may have heard about the octet rule. And that's what we're going to be talking about, is how do we get to this octet? Okay, so things try to lose electrons. These metals over here try to lose electrons to be like the nearest noble gas. And these nonmetals over here try to gain electrons to be like the nearest noble gas. And these guys in the middle try desperately to lose or gain electrons to be like the nearest noble gas. But it's often really hard for them to do so. Okay, so that makes it really hard to do what they need to do. And not all of these nonmetals are capable of losing or gaining as many electrons as they necessarily need to be able to get to that octet. Sometimes it's just really hard for them to do that. And so sometimes they're not able to lose or gain as many as they want. And so they have this situation where they have to share. So they can't necessarily lose or gain as many as they want. And so they get involved in a different kind of bonding, right? So if we're able to lose or gain, then we're involved in a kind of bonding called ionic bonding. Because if we lose or gain, we actually have a charge. And then we're called ionic bonding because we're charged and we're based on that charge. And, you know, we have fixed number ratios because of the charge that we have. But we can't always do that. So then we're involved in something else, a different type of bonding. Okay? So again, trying to always get to that octet. Now, not everything can get to an octet. The guys in that first row, this first row, they're not able to do that because they don't have space for it. So they only have the ability to have 2 electrons. Okay, so they're looking for what we call a stable duet. Okay, so they want to be like their nearest noble gas, which is helium. They only need 2 electrons, so they are called a stable duet. So that's a slightly different scenario. Okay, so some things are able to lose or gain electrons, like these guys in the first group. We lose 1 electron, most of us, so that we can become like the nearest noble gas. And so we're +1 when we lose 1 electron. And that makes us like the nearest noble gas. Like lithium can lose 1 to be like helium. Or sodium can lose 1 to be like neon. Okay, and we have the exact same electron configuration as that nearest noble gas. And so we can then be a charged species. And then we can bond with something that has a negative charge. When you make an ionic bond between the positive and the negative. That's awesome. So that's cool when we can do it. But it can't always happen. And so when we can do that, that's awesome. So ionic bonds had to be metal and non-metal bonds. So we can get something like an Na plus and say Cl minus, and then we get an NaCl. Okay, and that's a metal, non-metal. So that's ionic bonding between a metal and a non-metal. So anytime I have 2 ions next to each other, that's an ionic bond. Okay, so that's a complete transfer of electrons to form noble gas-like structures. Awesome. But I can't always do that. Now, if I have hydrogen and oxygen, right? I know that hydrogen wants to have 2 electrons, and I know that oxygen wants to have 8. Okay, hydrogen needs 2 because he's here, and oxygen being over here, he's in group 16. He wants to pick up 2 electrons to be like neon, so he wants to have 8. Okay, in order for him to do that, he'd have to pick up 2 electrons. But it's really hard for that to happen. And so when we try to make a water, then do we become an H plus and have 2 minus? And is that really what happens? Well, no, not really. That really isn't what happens. Okay. But we do have a situation where they can share electrons. Okay. So oxygen still wants to be able to access electrons from other places. And hydrogen still wants to access electrons from other places, but they need to be able to share those electrons to each be completely happy. Okay, and so they form something called a covalent bond. And that means that they're sharing those electrons. Okay, so they don't transfer them, but they're sharing. So that's called a covalent bond. And then it happens between 2 non-metals. Okay, so hydrogen, because he lives where he lives, notice that he's here, but he's not colored the same way as all of these metals. even though he lives here, he is still considered a non-metal. And so that's a non-metal to non-metal bond, and that's considered a covalent bond. Okay? So that's a little bit different. Okay? So when I think of covalent bonds, I think of them more like what happens when two parents get divorced. Sometimes there's a complete equal sharing of those kids, right? So sometimes they spend half their time with one parent and half with the other. It's not always the case. Sometimes they spend more time with one parent than they do with the other. And that happens to be the case when we talk about a hydrogen and an oxygen. Okay, oxygen has way more pull for those electrons than hydrogen does. So they spend more time with the oxygen than they do with the hydrogen. And so that's a situation where we spend like 80% of our time with the oxygen and 20% of our time with the hydrogen. So it's an unequal share. Okay. So we do have situations like that where it's not an equal share. Okay. But those are some of the things that we're going to be talking about is how do we know where they spend more time? How do we decide where they spend more time? How do they share these things? And what kind of rules determine? Okay. So how do we know where do they go? Where do they live? How do we know how they share? Those are the kind of rules that we're going to be talking about. And they're based on a number of different things. One of those things is electronegativity, which we've already talked about. One of those things is the Lewis dot structures, which we're going to talk about. One of those other things is the octet rule, which we'll be talking about in more detail. Okay, so those are the things that we're going to be talking about when we consider all of these structures. Okay, so let's get into the minutiae of how we deal with this. All right, so questions so far? Okay. So let's talk about a Lewis dot symbol. So first we're going to have to draw this for an individual atom, and then we're going to talk about how we put them together. So a Lewis dot symbol for a particular atom explicitly shows the valence electrons around that particular atom. So if we were to draw one for an oxygen, we'd be talking about the 6 valence electrons, 2 in the 2s shell and 4 in the 2p shell. So if we're talking about the oxygen, we draw the oxygen, the symbol for him, and then we have the 6 electrons that we need to draw around him. Now, just for clarity's sake, I'm going to draw those as X's to make them a little easier to see. So I've got 1, 2, 3, 4, 5, and 6. Now, is there any reason I drew them where they are? Not really. Okay, they're just where they are. Okay, that's where I put them. There's no real reason why I put them where they are. Okay. And eventually you'll come to realize that there are particular reasons that we draw them the way we do, but that's where I chose to put them. If that's a Lewis dot structure for O, let's talk about what we can do with H. Now, H has 1 valence electron because of where he is and how many electrons he has. So hydrogen is here, that's his symbol. But he has 1 electron that he needs to have next to him. I'm going to draw him as a dot, just to make it look different than the ones that we have for the hydrogen. I'm sorry, for the oxygen. Okay. So if I wanted to make a water molecule, I have an oxygen. I need to have 2 hydrogens. And so when we have an oxygen, 2 hydrogens, we're going to have the oxygen in the middle and 2 hydrogens around it. So we'll draw our oxygen just like we did before. This and this. We'll have 1 hydrogen here. This dot right there. And we'll have the other hydrogen over here with his dot right there. And now what we see is that that hydrogen with his 1 dot is next to the oxygen with his 1x. And then my oxygen with his 1x is right next to the hydrogen with his 1 dot. And that between the 2 of them, oxygen has access to 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And each hydrogen has access to 2 electrons. 1, 2, and this hydrogen has 1, 2. So everybody's happy. Oxygen has access to 8. Each hydrogen has access to 2. They're sharing, but everybody has access to the number of electrons that they wanted. Okay? So that's how we can take those Lewis dot symbols for each of these individual atoms that we have and put them together in a structure to show how we're sharing those electrons to make everybody happy. Okay? And that's what we're doing. All right, now this is a very simple example. We don't always draw them in exactly this way. This is a very simple way to do this. Okay, but this is how we show how that works. Okay, so questions about this? Now let's see how it can get a little more complicated. Now, let's look at oxygen. Since it's sharing 2 electrons with H, and 2 electrons for the 2 H's, and the lone pairs, there are 8 electrons around that oxygen. Sharing gives oxygen access to 8 electrons, and H has access to 2 electrons. Now, why the difference? H only has space for 2 electrons since its valence electrons appear in the 1s shell. So it only gets access to 2. And oxygen, to be like the nearest noble gas neon, needs to have 8 electrons, the 2s and the 2p's. Okay, so a total of 8. Okay, so that's what we were talking about with that difference. That first row only gets 2, everything else wants a total of 8. Cool. So questions so far? Awesome. So let's draw the atomic Lewis dot structures for carbon and oxygen. Now, carbon has a symbol of C, oxygen has a symbol of O. Carbon has 4 electrons based on his being right here. He has 4 valence electrons. And oxygen again being here, he has 1, 2, 3, 4, 5, 6. So carbon I'm going to take and put 1, 2, 3, 4. And oxygen I'm going to have 1, 2, 3, 4, 5, and 6. Again, I have 1 that's X, 1 that's O. No real reason to do either one, just so I can tell the difference. That's all I'm doing. Now I know that I can make CO2. I've written that a bunch of times. I can also have C and O in a number of different ways. So how can I combine C, O, and O to fulfill the octet rule? So I can combine 1 O electron and 1 C electron to make a bond, and the same on the other side, right? So how might that look? So I can take C, put him in the middle, and I can have this up here, and I can have this right here, and I can have this, and then my oxygen, that, and I can have this over here, and then I can have this here, and this here, and then an oxygen with this, and this, and this, and this, and this. Okay, and so what it says is that I've now got these 2 electrons that are available on this carbon. I have a bond that's been made between the carbon and the oxygen, a bond that's been made between this carbon and this oxygen, and I have 2 lone pairs on this oxygen, 2 lone pairs on this oxygen, and then I've got some random straggler electrons on these things. And we have 1, 2, 3, 4, 5, 6, 7 oxygen electrons available to this oxygen, 7 available to this oxygen, and 1, 2, 3, 4, 5, 6 available to this carbon. Nobody's really happy, are they? Nobody has access to 8. So that's not the best structure in the world, is it? Because nobody has access to as many electrons as they might want. So I look at that and I go, well, okay, that's not the best structure I can make. I mean, I could rearrange some things, couldn't I? I think I could. Okay. So I look at that and I say, well, I don't know that that's the best way I could do this. So I think that I want to rearrange some things. And one other thing that I could do is I could say, okay, well, what if I did this? And instead of having this oxygen with this single electron over here, what if I moved it over here? And I said I had this one, and then this and this. And then I had this and this and this, and this oxygen and this and that's all. Go away. And then this and this and this and this. So instead of leaving those stragglers out on the side, I pulled them into the middle. And so I took this electron for the top and this electron for the top, and I pulled one over here and one over here, and pulled the stragglers from the sides in and made double bonds. And now let's count those electrons again. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 here. And 1, 2, 3, 4, 5, 6, 7, 8. 8 around that carbon. And 1, 2, 3, 4, 5, 6, 7, 8 around that oxygen. And now everybody's happy. And so there are ways that we can redistribute those electrons to make things completely happy. Okay, so we have to expand our thinking to potentially look at multiple bonds. Okay, so it's not always as easy a picture as we might think it is. Okay, so how do we know what to do and when to do it? That's a good question. So we have to talk about how do we know when to do what. So that's part of the process we have to look at as well. So let's see if we can find some better ways to talk about how do we do what. So there are some rules, and the rules won't be available to you on the test. You have to remember them. So there are rules. So let's talk about a couple of things, and we're going to see if we can learn how to apply these rules as we go. So we're going to consider a couple of molecules. First molecule is PCl3. That's going to be on the next slide, slide 20. We're going to talk about NH3, which is on slide 21, and then BrO3 minus, which starts on slide 22. Okay, let's talk about PCl3 first. Now, the rules so far, what we're going to talk about, we're going to sum the valence electrons from all atoms, and we're going to take the charge into account. We're going to write the symbols for each atom. Connect those atoms with a bond, which is signaled by a line. Each line contains 2 electrons. We're going to complete the octets around the atoms bound to the central atom. And then we're going to place any leftover electrons on the central atom. And if there are not enough electrons to give the central atom an octet, then we're going to try multiple bonds. Okay, so that's what we're going to do first. So let's see what that looks like. By PCl3. So that contains a phosphorus and some chlorine. So I have 1 phosphorus. Each phosphorus, based on my periodic table, I find him right here. Now I count how many electrons are in this row. So 1, 2, 3, 4, 5. So there are 5 in that row. So that means I have 5 valence electrons available to him. That means I have 5 valence electrons from phosphorus that are being contributed to this particular molecule. I have chlorine. There are 3 of them. Each particular one is located right here. So that means that each particular one brings 1, 2, 3, 4, 5, 6, 7 valence electrons. So 7 valence electrons, 3 chlorines in total. That means there are 21 electrons that come from the chlorines, plus the 5 from the phosphorus. That gives me 26 total electrons that are going to come to this molecule from those places. So 26 electrons I'm going to need to put in. Phosphorus is written first, so he's going to go in the middle. I'm going to distribute 3 chlorines around him. Doesn't matter at this point where I put them. We'll talk about where we put them later. Okay, and why we put them where we put them. We'll do that in the next lecture. Right now, I'm just going to put them anywhere. The next thing I'm going to do is I know I have to have a bond that connects the phosphorus to each chlorine. That has to happen. Otherwise, they don't make a molecule. So I need to draw a bond between each one. Now, I can either draw that as a line, which contains 2 electrons, or I can draw explicitly 2 electrons between each one. Either way, there are 2 electrons between each one of these. So 2, 4, 6 are taken up by doing that. That means I have 20 electrons that are left over that will need to be distributed. Right? 20. Okay. So let's look at where those are going to go. So now I've got 2, 4, 6 that are taken up with those 3 bonds. And then I need to fill the octets for the guys around the center. Okay, so I've got 3 on the outside. They currently have 2 electrons that are associated with them, that's shared by the bonds with the phosphorus. So I need to have 2, 4, 6 that are added to each chlorine. 2, 4, and 6. 2, 4, and 6. So 2, 4, 6, 8, 10, 12, 14, 16, 18. And that leaves me with 2. So 18 were taken up by fulfilling the octets on those. And then there are 2 left over that go on my central atom. Okay? So 2 left, and I put those on my central atom. Right there. And that's because I have 2 left, and they have to go somewhere. So I have now put them on my phosphorus. That means I have none left over. So now I've taken care of everything that needs to go there. Okay. So I counted all my electrons. I made the bonds that I needed to make, and I counted the electrons that went into those bonds. 2, 4, 6 that went into the 3 bonds between the phosphorus and the chlorine. I fulfilled the octets for the chlorines. 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons are on those chlorines. That left me with 2 electrons that were left over that needed to go on the phosphorus, that central atom. And I put them there. Okay? That's the structure that I come up with for PCl3. So questions about that particular structure? Cool. So that's what we've got for that. Okay. So what's next? Well, now we're going to talk about NH3. Okay. So now we have NH3. So nitrogen. I have one of those. There are hydrogens. There are 3 of those. Now nitrogen, being where he is, 1, 2, 3, 4, 5 valence electrons on that nitrogen. Each hydrogen has 1 valence electrons. So a total of 3. That means I have 8 electrons that need to be distributed in that particular structure. Nitrogen is written first, so he goes in the center. I have three hydrogens to distribute around that nitrogen. So I just draw 3 of those hydrogens. And then I have 2 electrons to distribute between each nitrogen and each hydrogen. That takes 6 of those electrons up. And that leaves me with 2 electrons left over, which I then assigned to that central nitrogen. That then takes up all of my electrons, and that's what I have for my structure. So NH3 looks like that. Questions, comments, problems on that? Cool. Love it when that happens. And my next structure, BrO3 minus. Okay. So you've got a bromine that's going to go in here. There's one of those. I have oxygen that's going to go in here. There are 3 of those. And then there's a charge. That charge is a -1. So that's a -1, 1 electron that comes from that. Okay. Now my bromine being right here, we only count the S and the P. So there's 2 in the S, and then 1, 2, 3, 4, 5 in the P, for a total of 7. The oxygen, again, there are 3 of them, 2 in the S, and then 1, 2, 3, 4 in the P. That's, wait, no, can't count. Wait, no. 1, 2, 3, 4, 5, 6. There we go. I can count. 6. That's 18. And then, of course, my math sucks. So 18 plus 7 plus 26. And yes, I do need a calculator for that. So mock all you want. So there's 26 total that I need to have in that particular structure. I put my bromine in the middle because, again, he's written first. I have an oxygen, an oxygen, and an oxygen. Now I'm going to need a bracket around this whole thing because he has a negative charge. So I need to include that, because if I don't include that, then people are going to wonder, why is there an extra electron here? And it wouldn't make sense that there's an extra electron there unless I include the fact that there is a charge on this entire species. I include the bracket and the negative charge on it to show that there is an extra electron. Right. I need to have a bond that contains 2 electrons between each of these guys. So that takes up 6 of those electrons. That leaves me with 20 electrons that I need to distribute. Each oxygen gets 2, 4, 6. So that gives me 18 in total that I have distributed, leaves me with 2 left over. And those 2 go on my central atom. So that is the structure that I come up with there. And given the rules that I have so far, that's a perfectly happy structure, right? That looks perfectly fine to me. And so we go on our merry way and say, okay, we're perfectly fine with this. There's no reason to think that this is not perfectly fine. But something feels weird about this to me. And I'm like, okay, why does this feel so weird to me? Well, I don't know, it just does. So I come here and I say, okay, we're going to talk about something new, and that's a formal charge. Now, a formal charge is defined as the electrical charge difference between the valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis charge. So this is bookkeeping, that's all this is. And it says, okay, I am this particular atom, and I have 6, some number of valence electrons that I'm supposed to have, but right now I've been assigned this number. So what's my formal charge, right? So let's say I'm oxygen, and I should have 6 electrons, 6 valence electrons, but I only have so many that I've been given because of the structure that I'm in. What's my charge? Well, let's talk about that. Let's go look at the structure that we just drew. So valence electrons, formal charge. So let's talk about the formal charge for bromine and the formal charge for each oxygen, right? So we want to know the valence electrons. We want to talk about the bonding electrons and the non-bonding electrons, because that's what we were talking about for this formal charge. The first thing we want to talk about is the valence electron. So we talked about that. That's up here, right? So bromine has 7 valence electrons, and each oxygen has 6, all right? So that's what we're comparing to. Now, the other thing that we talk about with this formal charge, it says half of the bonding electrons and the non-bonding electrons. So we're going to subtract half of the bonding electrons and the non-bonding electrons. So half of the bonding electrons. So let's think about this for a second. Let's just say that we're talking about a bond, right? Bond has 2 electrons in it. And if I'm a particular atom and I'm talking about this bond, technically speaking, half of those electrons can be assigned to me. So if I have a bond, one of those electrons is mine and one of them belongs to the person that I'm sharing it with. So half of them are mine. So this bromine has 1, 2, 3 bonds, and half of those 6 electrons belong to him. So 3 of them are his. Each oxygen has 1 bond, 2 of those electrons in that bond, and half are his, so 1 electron belongs to him. Okay. Then we're going to subtract the non-bonding electron. So the bromine has 2 non-bonding electrons. That lone pair belongs entirely to him. And then these oxygens each have 2, 4, 6. So if I look at the formal charge for the bromine, he should have 7, and he has 5. So his formal charge is plus 2. Each oxygen wants 6, but actually has, at this moment in time, 7. So each one has a minus 1 charge. So overall, this molecule has plus 2 for the bromine and minus 3 for the oxygens. So overall is a net 1 minus 1 charge, which matches what it has, which is good. But that's a lot of charge all over the place. So we're looking plus 2 here, minus 1, minus 1, minus 1. That's a lot of charge. And that's the problem. What we want is for the overall charge to match what it should be, but not to have charge everywhere. We want to minimize that charge. And we can do that. Remember, once upon a time, we moved some electrons to make some double bonds? We did that because we thought that it might be a good idea. We can do that here. We have some electrons that we can move. So we can actually move some of these electrons that are on these oxygens. Remember, each oxygen has more electrons than it needs because each one has a minus 1 charge. So we can move some of these electrons, take them from these oxygens, and say, you know what? I'm not going to be as selfish as I'm being right now. And I'm instead going to take one of these lone pairs and I'm going to make another bond. So I'm going to go like that. And so now I have a double bond with this bromine. And so now I have changed that formal charge. And so now instead of looking like this, I now have 2 different types of oxygens. This oxygen right here is going to be an oxygen 1. And this is going to be oxygen 2. And the oxygen 1 still looks the same. But the formal charge on the oxygen 2, we want to be 6. We're now minus 2, or 2 electrons, and then minus the 4. So that one has a formal charge of 0. But that bromine in the middle looks completely different than it did, right? So it has the 7 that it, that it wants. That's what it wants. But it now has the half of the bonding. So 1, 2, 3, 4. And then its lone pairs is minus 2. So it now has a plus 1 charge. And so now we've changed that so that we're now looking at less overall charge. So this is a plus 1, minus 1, and minus 1. And so we've minimized that charge because this one is now a plus 0. Okay, better, but still not ideal. Because we do that one more time, if we change one additional oxygen, so it's no longer a -1, and we change this to be like this, and move this over here, and now the bromine is no longer a plus 1, it's a plus 0. This is a plus 0. And then only this oxygen down at the bottom is a -1. The only caveat is that now we have 2 different types of oxygen. And that means that things are a little bit different because we now have a situation where they're not all equivalent. And so why is it that only one of them is different than the others? So now we have to talk about how it's not really that one of them is different. They're actually still all the same. It just looks like only one of them is different. And so we have to talk about what kind of structure that is. And what we call that is a resonance structure. So even though it looks like this one is different, it turns out that this single bond and these double bonds move really, really fast. So this single bond actually exists in all of these locations at a given moment. And it's not really that it's a single bond in one place and a double bond in the other places. It's actually more like 1.5 bonds in all of those places. So we have to be able to show how that really looks. And we do that by drawing multiple structures. And so what that looks like I know I haven't. Give me a second. I'll come back to those other things. Is this right here? Where we have double bonds down here and a single bond here, single bond here, double bonds here, and then single bond here, double bonds there. Okay, so these are the resonance structures of this particular molecule. Okay, so we have to show that they're all equivalent. It could be any of those locations. All right, so that's what we have to do. Now, this is not that complicated. It's just tedious, in my opinion. That's how this works, is we have to make sure that we've shown that that is equivalent in all of those places. Okay? And I said I'd come back. What I wanted to do was to show you the formal charge on each of these guys. So what I'm going to do instead of doing it that way is to come back and show you on these structures what the formal charge is on each of these. So I have these structures that I was looking at formal charge for. So we can talk about the formal charge on P and the formal charge on Cl. So phosphorus, again, valence electrons, he wants 5. Cl wants 7. Non-bonding bonding electrons, he gets 1, 2, 3 from the bonds. And our chlorine, each one gets 1 from those bonds. So 1, half of those bonds. Each one gets 1. And we then take the non-bonding electrons for the phosphorus. He's got 2. And so his formal charge is 0. We talk about our chlorines. He gets 2, 4, 6. So each one of those is 0. So there's no formal charge in that molecule. Cool, we love that. We talk about our NH3. Yeah, nitrogen wants 5, hydrogen wants 1. For our bonding electrons, nitrogen gets 1, 2, 3. And then his non-bonding is 2, so he has no formal charge. Our hydrogen gets 1 from his bonding electrons. He has no non-bonding electrons, so he has no formal charge either. Cool. Love it when that happens. And we come over here and we look at this particular structure, this first one that we drew. We already did the formal charge on this. Okay, so we've talked about what is the formal charge that we talked about for here. Okay. So formal charge is not related to an ionic charge. It's just bookkeeping. Okay, so it's just a way for us to determine how happy is the structure that we've drawn. Do we need to consider making a move with those electrons to make a better structure? That's all it's for. Okay, do we need to make a double bond? Do we need to make a triple bond? Do we need to look at other structures? That's all it's for. Now, let's talk about CN minus. So we have a carbon, we have a nitrogen. There's one of each. Carbon has 4 valence electrons. Again, he's right here. So 1, 2, 3, 4. And then nitrogen's right next to him, so he has 5. And then since it's a minus, we have 1 electron from that charge. So we have a total of 9 electrons from there and 10 for the charge. So there's 10 electrons that we need to distribute. This is going to be in brackets because of that charge. We have a carbon and we have a nitrogen. And we start by making 1 bond. So there are 2 electrons that go in between the 2 of them, right? And since carbon is written first, he's considered our central atom. So we have 2 electrons that are taken up there. We then have 8 electrons that are left. So we have 1, 2, 3, 4, 5, 6 that are distributed around the nitrogen. And that leaves it with 2 that we put on this carbon. Okay, so that's the initial structure that I would draw based on the rules that we have so far. Okay, if we look at our formal charge, the number of valence electrons for our carbon is 4, and for our nitrogen is 5. We subtract the number of electrons in each bond. Each one of them gets 1. And then the number of non-bonding electrons on the carbon is 2, and on the nitrogen is 6. So 4 minus 1 minus 2 gives me 3, which is a plus 1 charge on the carbon. And on my nitrogen, I have 5 minus 1 minus 6 is minus 2, which is a net negative 1. Okay, so now in theory, that looks fine, but I know that's not really fine. I understand that. So I need to look at moving some of those electrons to minimize that charge. Okay, so I know I'm going to move some electrons. I'm going to start by taking one of these pairs of electrons and putting it between these guys. Okay, so the first thing I'm going to do is I'm going to take 2 of these electrons and put them in here. And I usually do that with the one that's on the end. So I do that. Now, when I do that, that changes some things. So I look at my formal charge again. Change all of this to see what my new formal charge is. So I now have 2 electrons in the bonds, and the number of lone pair electrons on my carbon has not changed, but it has on my nitrogen. So I have carbon has 4 valence electrons, has 2 bonding electrons, 2 non-bonding electrons, so he's a 0. And my nitrogen, 1's 5, -2, -4 is still -1. Okay. But I'm still looking at this, and it's still not the best structure that I can get. It's still not, we still have some ability to change that. Okay. And change things up a little bit. And so what I'm thinking we're going to do is to say, okay, let's see if we can minimize this a little bit more. And so what I'm going to do is move another pair. And I'm going to move one more pair so that I can make another bond. So I'm going to put another pair in here. And I'm actually going to take and move both of these so that that goes like that, just for aesthetic reasons. That gives me a -1 there. We now have 2, 3, 2, that's at 0 there, and a -1 there. And we've reversed this a little bit, but that's okay. And that is the best structure that we can come up with between these. Okay. Now, why do we know that that's the best structure? Because it has the best arrangement of electrons that we can come up with for this set. And I know that that has the greatest stability that I can come up with for this set. So that's what I come up with for that guy. Now, I'm just going to tell you that, and you're not going to be asked to draw this one. So, but that's what we come up with for this guy. Okay. So questions on that one. So again, we want to make sure that we're checking that formal charge to see if we can minimize the formal charge that we get on these structures. We want to make sure that we're getting it where we get it. And we also want to make sure that when we have a situation where we have formal charge, that we minimize it as much as we possibly can. All right. So, cool questions, comments, problems with any of that. And if we end up with a structure where we have a multiple bond in one place and a single bond in another place that are effectively equivalent, then we want to draw them so that they are equivalent, i.e. that there are multiple structures that we have for that. Okay? So, when we talk about O3, we have 18 total electrons. We have 2 bonds that are formed. That takes 4 of those electrons out. That leaves us with 14 electrons that we put around that. Each oxygen requires 6 more electrons. That leaves 2 electrons to put on the central atom. But that doesn't leave us with an octet on that central. Okay. So what does that give us? Okay. So end up with those 2. So again, 2, 4, 6. That does not give us with the best structure. So we know we're going to have to make at least one double bond. So we put this in like this, and that gives us this structure here. Okay, not ideal. We know that we have formal charge on this, so we're going to call this oxygen 1, oxygen 2, and oxygen 3. So on oxygen 1, we have our valence electrons on each of these is 6. On oxygen 1, we have 2 electrons from the bonding electrons. We have 4 from the non-bonding electrons. So that's a 0 charge. On oxygen 2, we have 1, 2, 3 from the bonding. We have 2 from the non-bonding. That's a +1 on this guy. And then from oxygen 3, we have 1 from the bonding electrons, and then 2, 4, 6 from there. So that's a -1. Okay. Now looking at oxygen, where he is, he's in the second row. So he can only have a certain number of electrons around him. He cannot have more than 8. We cannot violate that octet rule because he doesn't have any empty d orbitals with which he can violate it. So we can't give him any more than that. So this is the best structure that we can come up with for this. But because I have 1 double bond and 1 single bond, we know that we have to have a resonance for this. And so what this actually looks like, the other structure that we end up with, is this one. Okay, where the single bond is reversed. Okay, and what we end up with is double bond on one side, single bond on the other side. And there's an interconversion of those. It's very, very fast. And we give this a delocalization. Okay, this is another way to draw this. Okay, so I don't care how you draw this, whether you draw this and this or this. Either way is fine. Totally up to you how you decide to draw it. Entirely up to you. Okay. Either one is perfectly fine. All right, we tend to use the second one more in organic chemistry, and I'm okay with it if you choose to use it. It's available out on the interwebs. So if you want to use that, that is okay. All right. Now, are there exceptions to the octet rule? Absolutely. I wish there were not, but that is the way that this works. Some things that we have, a couple things we've already talked about, hydrogen and helium, they have a duet, not an octet. So that's one thing. Nitrogen often is a violation of the octet rule, and that's because it has 5 valence electrons, and so it often is a violation of the octet rule because it's an odd number. Okay, so we often end up with situations where it cannot get to 8. Okay, so that's a situation where we often get a problem, right? NO, because of that, it has only 11 available electrons, and that gives us a problem for that. All right. Other things. BF3. Let's talk about BF3. So, boron and fluorine. So, boron is right here. 1, 2, 3 valence electrons for boron. And then fluorine, there are 3 of those, and there are 7 valence electrons because he's a halogen. So there's 21 from there. That gives us a total 24 electrons that we need to draw for that. I'm going to put boron here and the fluorines around it. 1, 2, 3, 4, 5, 6 electrons in the 3 bonds that makes. So that leaves me with 18. If I'm not mistaken, and I don't trust my math, so go. I actually did it. So now I'm going to fulfill my octets. 2, 4, 6, 8, 10, 12, 14, 16, 18. And that's all well and good, except now I've got 2, 4, 6 in those bonds, and then 2, 4, 6, 8, 10, 12, 14, 16, 18, fulfilling those octets, and then boron is left with this hole. So there are only 6 electrons around boron. So he's a violation of the octet rule because he does not have a full octet. Okay. So boron is a violation. But then there's NH3. Remember NH3? And he looked like this. And he's got this extra pair of electrons on the top of him. Now, the extra pair of electrons can come in here and make a coordinate covalent bond to boron, or it donates both electrons to the boron that is missing a pair of electrons. And so this is a Lewis acid-base reaction where we get this pair of electrons being donated from nitrogen to boron. This is a Lewis base acting on a Lewis acid, okay, where we get that donation of electrons. And so they fulfill the octet by sharing that pair of electrons. Okay, this is a wonderful association because they both get to be happy. You know, nitrogen gets to give some, boron gets to take some, everybody's happy. Okay, but this is one of the things I love to talk about because this is a way for both of them to get what they need by sharing. Okay, so this is a situation where nobody had what they needed. You know, there was not a way for boron to be happy, but then nitrogen came along and said, hey, you know what? You ain't got enough. I'll give you some. Okay, so this is a way for them to make that happen. All right. So that is a violation of the octet rule that we can then find a way to deal with. And there are other ways that we can get exceptions to the octet rule. Let's talk about P at 5. And we have our P, there's one of them, and P being where he is, he's under nitrogen, so he has 5 electrons. We have fluorine. There are 5 of them, and each one has 7 electrons, so that's 35. That brings a total of 40 electrons that we're bringing to this. Phosphorus is in the middle, and there are 5 fluorines around him. Last time I counted, that means that there are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in the bonds. And that's a violation of the octet rule because there are 10 electrons around phosphorus. That's a problem. Well, no, not really, because that's what he does. And phosphorus, being in this 3rd row, has empty d orbitals that he can use to make that many bonds. So he can do this. So it's perfectly acceptable for him to do that. Now, the other thing is that we have 30 electrons that are left over, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. And they're all used up when we make the octets full. So everybody's happy when I do this particular structure. But it is a violation of the octet rule because we've made more than 5 bonds, or more than 4 bonds. We have 5 bonds. And so that's a violation of the octet rule. So we have some things that can make more than 4 bonds. It's not outside the realm of possibility, but it is by definition a violation of the octet rule. Okay, so those things are violations as well. So anything from row 3 down can do that, but it is a violation of the octet rule. Okay. Now, let's talk a little bit more about water. We talked a little bit about water already. I talked about the fact that water has 2 lone pairs that it's got on it. And any way we do this, okay, what we have is that there are two bonding pairs, two non-bonding pairs, and those two non-bonding pairs, no matter how I do this, all end up being on one side of the molecule. Okay. And what this ends up looking like when we look at the electrons and how they're distributed is that we've got one end of this molecule that has all of the electrons on it, and one end of this molecule that is very deficient in electrons. That's what you're looking at here is an electron diagram map. Okay, and all of the electrons are in this red part, and this blue part here has very little electron on it. Okay. So we have a partial negative end of this molecule and a partial positive end of this molecule. Okay. That's actually really cool because that pull of electrons to one end versus the other end means that this molecule is polar. Okay. That polarity in the molecule gives us really interesting properties. And that's why half of the things on the face of the planet work the way they do. And if they didn't, life would not work the way it does. That's awesome. I mean, that's why we are the way we are. And I think that's amazing. But it's also why a lot of things work the way they do. And polarity, like dissolves like, the polar things go into polar things, non-polar things go into non-polar things. It explains a lot of the things that we have. When we talk about intermolecular forces, this will be a huge part of what we're talking about, is the polarity of those molecules has a lot to do with why they behave the way they behave. Okay, and this has everything to do with the three-dimensional structure that we'll talk about for this molecule in the next lecture. Okay, so water is weird. We're going to keep coming back to the fact that water is weird, and that's why it's special. So this is a very special molecule, and this is where we start talking about exactly how special and how weird it is. So, cool. Now, remember we talked about the fact that it's a polar bond, so the electrons are not shared evenly between the hydrogen and the oxygen. They spend more time with the oxygen than they do with the hydrogen. So they spend more time on one side than they do on the other side. It also means that those electrons are yeah, that was it. Sorry. Now, we aren't going to do the calculations that go with the electronegativity. We're only going to talk about them in the qualitative sense, not the quantitative sense. So we won't do the calculations. We just talk about them in the fact that they spend more time on one side than the other side. So don't worry about the numbers. Now, the fact that this is a permanent distribution is important. Some things have a permanent distribution where things are uneven, and that's called a dipole moment. This has a dipole moment. It's a permanent dipole. Some things don't. So CO2, even though the oxygen has a pull for those electrons more than the carbon does, there's an oxygen on each side of that molecule, right? So we have an oxygen here, carbon in the middle, and oxygen here. And there's a double bond here. And so there's a pull of electrons this way and a pull of electrons this way. But because they're pull on each side, there's no net pull in either direction, right? Not useful. This, on the other hand, we have a net pull towards this end of this molecule, all in this direction. And so that's a permanent pull in one direction. That's called the dipole moment. This one does not have one because it's an even pull in both directions. So that's different. We need to be able to talk about that. And that's part of what we'll talk about when we talk about the three-dimensional structures of these molecules. Okay, so in the next lecture, when we start talking about what they look like in 3 dimensions, we'll talk about whether or not they have permanent dipole moments. Okay. One other thing we need to talk about. We've talked a little bit about multiple bonds. Multiple bonds are great. Now, multiple bonds mean that we have more electrons in those bonds than we would normally. So a single bond is 2 electrons. Double bonds are 4 electrons. Triple bonds are 6 electrons. The other thing is that as we get more electrons, they get a little bit shorter. So a single bond is long, a double bond is shorter than that, triple bond is shorter than that. Okay. But here's the other thing. Those multiple bonds occur in the same physical space. So they have to exist in the same physical space. So even though I have two bonds there, it doesn't count like two bonds. It counts like one bond because I have to exist in the same physical space. So I can't count them as two different things when they have to exist in the same space. Okay. So when we talk about how many bonds exist, we count multiple bonds as if they were one bond. Okay, so when we get into the next lecture and we're talking about that, multiple bonds count as if they were a single bond. Okay, those lines count as if they were two electrons, two lines count as if they were four, three lines count as if they were six. Okay, so there's that. Questions about that? So that's everything I have in terms of bonding and dot diagrams. That will lead us into our discussion of valence shell electron pair repulsion and what that looks like in three-dimensional space. So I hope that's everything that you need from this, and we will get into that next lecture shortly. Thanks, guys.